Because again, if you add another byte onto the RAM addresses, you could, so clearly, back in the days of the 32-bit chips, you could have put 8 gigabytes of RAM in a computer, but they typically didn't because it would have required a bigger address space, and each address wouldn't fit through one cycle of the chip. See what I'm saying there? So for a good while, you wouldn't put more than 4 gigabytes in a normal computer. There were ways around that. You could still get bigger RAM chips, but it required some extra work. So basically, this is has an 8-byte word size, which means it's about a max of 2 to the 64. If I remember how much RAM that could support using 8-byte RAM addresses. It was a term I didn't even know. It was a zettabyte.
Yeah.
It was some number of zettabytes. 18 zettabytes. So it was 18 zettabytes.
Damn. That's a lot of memory.
However, if you look at these address spaces used by the size of, so what would the size of this address space be? It's not using 8-byte addresses. So our C program used 6-byte RAM addresses, which can support how much RAM? It's 2 to the, what's that, 48, which is approximately, now this was in the terabytes, huh? 180 terabytes? 280 terabytes? So the question we left off with is why are they not using the full 64-bit addresses? Because the chipsets can easily process those full 8-byte addresses. Well, the easy answer is we don't need that much RAM. We almost probably don't even need that much RAM. So these 6-byte RAM addresses are more than enough for the foreseeable future. But things move fast. That's what Ferris Bueller always said. Things move real fast. And you know, there might come a day when we want more RAM than this 15 years from now. And so they could easily, using the current chip architecture, up these addresses instead of 6 to 8 bytes. And what's the reason they probably don't just use 8 bytes? I mean, when they switched to 64-bit chips, all these operating systems could have said, heck with it, let's just use the full 8-byte address space. And that would seem logical. Why do you suppose they didn't? I had to do a little bit of research to figure that out. That puzzled me. I'm like, why are all these Linux machines only using 6-byte RAM addresses? When it wouldn't be hard to use 64. I mean, from a programming standpoint, that would be no harder. And the easy answer is this is more than enough RAM, but there's got to be more to it than that. Because why not make it have room to grow, right? Anybody remember what we talked about?
Money.
Huh? Yeah, there's a lot of other stuff in there besides the CPU. There's these memory controller chips. Like, it used to just be a CPU that did everything. Now these modern architectures, they have these memory controller chips. So so the CPU doesn't have to be controlled and writing stuff from the RAM to the hard drive. They dump it to a memory controller chip that writes things. So there's other subsidiary chips that do some of the grunt work, leaving the main processor running processes. So probably it was just too expensive to make all these subsidiary chips handle these full ads. So anyway, if they would have used the full 8-byte address space, all the extra components would have had to have been upgraded and probably increased the cost of your computer by hundreds of dollars. And there just wasn't any need to do that because the 6-byte addresses are more than enough. So anyway, that's what when I first built this program, I had to think through all of this because I wanted to know what was going on. That's pretty interesting. Okay, so I'm going to show you something else that's pretty cool with processes now. So here I've got my my shell open here, and I'm going to back up a little bit, and I'm going to look at these. So these C numbers refer to the chapters in the Modern Dive book. So there's a couple of sample programs he gives out in the C4 processes. One. We'll look at those in a second. But actually he gave out some in chapter 2. If you look at the Modern Dive book, we just read 4 and 5, right? Yeah. Chapter 2 was just an introductory chapter that kind of hit a bunch of topics. And he gave out some programs with infinite loops in them so that you could kind of see what programs competing for CPU time would do. But those were dangerous. I can't believe he put those in a textbook. Because if you guys got a hold of those programs and started running them on the server without killing them, you would have a bunch of runaway processes that would, in infinite loops, that would run indefinitely. So I can't believe that he gave those out to students. So I rewrote them as my programs, which are less dangerous. They're not infinite loops forever. So so I'm going to go to these programs and let's see what's in there. These are the same ones available for download as a zip. So from lesson 4, you can download these and run them yourself if you want. Let's see what's in there. Okay, let's take a look. Let's go to my code editor and see what's in there. So let's do the README, and let's see what the C program is in this common library. Hang on, I got too much stuff open. Okay, so what the README in there says is it says how to run one of these programs. It says don't use, I guess the author gave them out in chapter 4 actually. Don't use the author's programs from chapter 4. They'll run forever in the background. You could really bog our server down. And so I rewrote them to be a little safer, and you'll see what it does. It's required, you have to pass in an argument, and it's gonna have it's gonna have a loop that runs for 1 second. So if I just ran the loop without that, it would just print a bunch of stuff 60 times. It would just print something 60 times in a fraction of a second. But this causes it to wait on each pass of the loop for 1 second. So that spin function is like an infinite loop for 1 second. And so what it does is the loop's going to run from 1 to 60. Each pass of the loop, it's going to infinite loop for a second, and then it's going to print the argument that was passed in. So literally this is going to go 60 times once a second, and then it's going to quit. Whereas the way the author gave the program, it would run forever. So it's an interesting program, so I'll show you what it does and then you'll understand better. So let's go back to the shell, and I'm going to run CPU. Let's see, so it's already compiled. CPU.o. I'm going to pass it in a capital A as an argument, and you'll see what's going to happen. It's going to print a capital A once every second. But there's an infinite loop going in between each of those, not infinite, but a semi-infinite loop for 1 second. I don't know why I'm calling that infinite. It's a runaway loop that runs for a whole second doing nothing. And I'm going to break out of that process so it doesn't run. We don't have to run it for the full minute. Hang on. There. So I broke out of that. Now, what this README tells you is that instead of redirecting the output back to the shell, if you run the program and put an ampersand after it, it will run in the background more like a service. So watch this. So here, I'm going to copy this out of here. So after I get this running in the background, this command is a listing of the running processes, and I'm just going to grep it for this CPU program. So this program is called CPU, right? So I'm going to run it in the background, and then I'm going to grep for the process, and you'll see what's going on. So let's copy that in there. I'll just run it and put the ampersand after it. And it gives you the process ID. Well, for whatever reason, it's printing back to the shell, which surprises me. But you know, I think I might need to go to a different shell to kill it. But here, anyway, here's the process ID. I copy that. I'm going to go to my other shell, and I'm going to say kill that process number. Notice it stopped, terminated. So I got that process running, and I went to the other shell and killed it, okay? Now watch what I'm gonna do next. I'm gonna start two distinct processes in the, well, I guess I didn't run PSAUX while I was doing it, so let's try this again. So let's go to the other shell and run. So where is it? Here's the process for that's running. So here's the process ID. And so that's going to keep running for a minute. If I waited a minute, that process is going to go away by itself because that program terminates after. All right. So you can see that it's running here. Let's see. It's still running. How long do you think it's been? Huh? Can you tell? Oh, 40 seconds. Oh, I didn't even see that. Now it's been running for 51 seconds. That's pretty bad. Like, the author literally gave programs that would keep running forever. This one quits after 60 seconds. It's gone now. So that's pretty cool. You see what this program does. And why are we doing this? Well, I'm going to show you. So what I'm going to do, if I go back to the README, it tells you that you can get two instances of it running at the same time. One instance is going to print out A, and one instance is going to print out B. So I'm going to start up two instances of this. What just happened? Hang on a second.
Are you in the same directory as Alicia?
Say what?
Are you in the same directory as Alicia?
Ah, you're right. I was in the other shell. Thank you. I knew there was something. I wasn't in the same directory with the program. So here, there we go. So now it started two different processes. They're running in the background. So look, it's alternating between the two processes. But watch this. I'm going to run this command over in this other shell called htop. And so what this htop command does is it prints out the CPU usage of all the programs running on the system. And you can see that these programs I have running are literally taking up almost 100%, 99 point something percent. Whereas some of these other things, like the MySQL processes, you can see them sometimes jumping in and taking like a 0.7% of the processor capacity. So what's going on there? Like, I know football players can give 110% at practice, but how can we be using 200% CPU capacity? Here, it quit actually after a minute. So now we can see the normal processes running on the computer, and most of them are taking up a fraction of it looks like the HTOP program is taking up the most CPU. Just monitoring all the process, that thing at the top is the HTOP program most of the time. Occasionally something will beat it, like the MySQL just beat the HTOP program. But here, let's go back and start rerunning the other ones again and see if you can explain that. All right. Okay, now they're running again. Anybody want to tell me what's going on there? All right, I'm going to stop the HTOP program. Let's run another program called LSCPU. This is a program somebody wrote to list statistics about the CPU. So it's an x86 64. It actually could run in a 32-bit mode if it wanted. Little Indian just is talking about the byte order. Here we go. There's the key line right there. There's 2 cores that this Ubuntu system has. So there's 2 separate cores that can be running programs simultaneously. And you can see it's got the caches and how fast these chips are and blah blah. Intel Xeon chips. So I don't care about the rest of this. So let's go back and get my program running again. And now let's go back and run HTOP. And tell me what's happened. Now how 1 got up to 101% right there, I don't know the answer to that. Did you see that? I have no answer to that. But is this bad? Tell me what's going on. So this little cheesy program I wrote is literally taking up almost 100% of each CPU capacity. It's like, is that bad? Well, it's because there's 2 of them. 1 can run on each core. That's why it adds up to 200%. So it's 100% of each core. But is it bad that these are malicious programs, basically? Infinite loops for a minute is essentially what they are. So is the operating system doing something it shouldn't? Should it detect that these are malicious? What's actually happening is the operating system is doing its best to give everything a chance. You notice how those are getting interrupted by those 0.7s? So it's giving as much processor space to those 2 rogue programs as it can, but every time something, when we study scheduling, what you're going to find, well, those processes are gone now. I'm not going to start them again. But what you're going to find is those programs were CPU hogs. So the scheduler knows that, and it gives them a lowest priority. So anytime some other non-hog wants to run, it gets put to the top long enough to run. Those other processes were just taking up a fraction of a second though. So anytime the system needed to do something else, it would get elevated to the top, which is what all those 0.7s are and stuff. But then, as soon as the processor was idle again, it would put those memory hogs back on it. And that's what it's supposed to do. The computer's supposed to run as much stuff as it can as quickly as possible. So it allocates 200% or 100% of each core to those programs as much as it can. And that's just what computers are supposed to do. Its job is to execute all the jobs as expeditiously as possible. So That's kind of interesting, huh?
What would happen if you ran 3 of them?
What would happen when?
If you ran 3 of them, so
Well, he said, that's a great question. I love the inquiring mind. Let's, how about I one up you? How about we run 4 of them? You tell me to run 3, I'll
I'm
run
looking for
4
that.
of those puppies.
can we do 5? I want to
Don't
see like
push
an
it,
odd
buddy.
one. No, just so it's odd and it's not like split this way.
We could. Hang on, I'm gonna run 4 of them. I'm gonna give them different, different output letters. Okay, that's 4 of them. Yeah, and there's the process IDs. Let's run. It's pretty predictable. You wanna explain, Ahmed, what that's doing?
I mean, it splits the process for on like it splits them for the cores, and then as you said, like it tries to maximize how much.
Yeah, it's you know, when necessary, it's still these are popping down to, you know, a smaller percentage, but sometimes but it's letting all 4 of those processes share those 2 cores as much as possible, often giving 50% of each core runtime. And so again, that's the scheduler doing what it's supposed to do, trying to run all the crap that's on the computer, all the jobs as efficiently as possible.
I guess what I was asking is like for when it's odd, does like one process like do they all split
Oh
in the
yeah,
same?
I don't know. I don't know if you'd get 2/3 in there, or but yeah, let's try the odd number because those are done running anyway. Well, here, let's just take one of them off. So we'll run 3. Yep, it's doing the thirds. So now it's splitting those, giving roughly 2/3 of the processor cycles to each one, but still elevating those other ones, like those 0.7s. So it's kind of interesting. I thought you'd find that interesting. So no talk of, you know, processes and CPUs is really complete without watching what the scheduler does when you have these essentially malicious programs running. It doesn't see them as malicious. Well, it does, but it just sees them as hogging the processor, and it still tries to get them done. Why it occasionally adds up to over 200, that I do not know. There may be, maybe these are averages over some milliseconds or something. That's probably what it is. It's not any instant point in time. It's an average over the last millisecond. Believe it or not, you see, it's swapping these processes. So it's not actually 2 of these things sharing one core at the same time. You can't do that. What these are context switches where it's popping those on and off. And if it's 50-50 on one core, it's literally popping those on and off real fast. And it can do those context switches in like on order of 10 to the -6 or microseconds. So what it does is it takes all when one of them is running on the CPU and it has to put the other one on for equal time sharing, it takes all those CPU registers and stores them in a C struct. That was shown at the end of the last chapter. And it puts the other one on, restoring it from its struct, and it literally does that in microseconds. So these are probably averages over milliseconds or something, which is why it can add up to a little more than 200%. So anyway, all right. So enough on that. That's pretty interesting. Let's see what else we want to talk about. Oh, so here's what we're going to do now. That was a good wrap up from last time. Now we've got all this new forking business from the chapter for today. And I have a really forking cool worksheet that we're going to do about forking. And but we're not going to get to that today. So let's talk conceptually about what the fork thing does, and then we'll do the forking worksheet next time. You guys must have a dirty mind if you're giggling about that. That's all I have to say.
Yes.
Okay. So pictures. And they did a, you know, they always said a picture's worth 1,000 words. They did a scientific study and they found out it's only about 987 words, but that's close enough. Every now and then I'll tell that to somebody and they'll say, really? But you guys were on to me. Words and okay, so here's what we'll go through some slides quick. And I'll supplement this with a picture on the board. So of course I didn't post these slides until you were taking the quiz. What was the acronym that the author used when, if you were Linux people and somebody asked you a stupid question at work?
RTFM.
Read the freaking manual
Yeah.
page or something.
Sure.
I thought that was funny. You go bugging somebody at work, how does this command work? Well, read the freaking manual page. All right, so anyway, so the first question, it should come no surprise since we studied POSIX, which was the Portable Operating System Interface, where they tried to make everything uniform across all operating systems. It would be madness if you couldn't do forking off processes if that was totally different on each type of operating system. So it's no surprise that these process stuff and forking comes from POSIX. So the good news is it works very similar on any operating system because they figured out the right way to do it many years ago. What in the textbook, what did the author call that? Lamson's law. That was a dude that just tended to get it right. So they figured out the best way to fork off new processes, and they tried a bunch of crap. And this is just how it works with the fork and followed by exec. So, and it's good that that POSIX made that pretty uniform across all operating systems. So that was the first question on there. I'm guessing probably that's the least. I'm expecting a lot of you got a lot of them right, but that's probably the most missed one that will be on the reading quiz. But whatever, that's why I ask a lot of questions, in case you happen to know that and not something else. So here's the code, and I think you saw how this works. So if you're running a program that forks off another process, you've literally got two chunks of code in there, one that's going to run in the child and one that's going to run in the parent. So let's talk about how this works. So let's talk about a parent process. And so we've got the code at the top, and there's this thing called a program counter. And the program counter is a register on the CPU that just indicates how far through the machine code it has progressed, right? It has to run all the code in the compiled version. So here the process counter or the program counter shows it's about, I don't know, halfway through running the code. And there's another program counter at the bottom. So the first thing that's called is main in the stack at the bottom. And what we're going to do is now suppose main calls the fork function. So now if there's a fork call in the main, that goes on top of the call stack, right? Because that's the most recent function call. And what happens when the fork is called? Anybody? What do I need to draw on the board to show that the fork is called? Something radical happens here. A whole new process that looks just like the parent springs into existence. So the fork function calls this whole new, so basically there's also another counter here called the stack pointer, I think it's called. The stack pointer is where it's executing in the stack. So anyway, it makes an exact duplicate for the child, So this is an exact duplicate. Almost. In other words, it's going to have the same code. The program counter is going to be at the same spot. So it'll be the same spot. I don't know if it actually duplicates the main function call down here. That's beyond my knowledge, but it picks up in the fork call, and basically it's running the child process at the same point as the parent process. Now the fork call returns something a little bit different into the parent than it returns in the child. That's why I have exact in quotes. What does the fork call return to the parent? Yeah?
The PID of the child.
Okay, it returns the child, PI, process ID. Those were those, when I killed that rogue thing, when I did kill, that was the process ID. So literally, like when we were running the top program, we saw those process IDs. What does it return into the child?
0.
0. Why is it important that the fork returns different things depending upon which process? Gabe? Yeah, well, it's running the same code. So how's the same code gonna know what to do in the parent versus what to do in the child? So that's where back to this program right here, is if it's running the same code. Now the first part of this, can you see that in the back, or need to blow it up?
Blow it up.
Blow it up? How about that?
That's fine.
So the first part of this just says if it goes bad. I've never even seen it go bad. But basically you've got this if-else where if the process ID returned to 0, you know you're in the child process. Otherwise, you know you're in the parent process. All right? So, well, let's ask a couple more questions since we have this picture up on the board. Which one of these is going to be running on the computer, on the CPU?
If there's no way they're good, then both sides?
Yeah, if there's no call to in the parent to wait for the child, you don't really know because it's up to the scheduler. It's completely up to the scheduler. Like in a 2-core system like we were just looking at on the computer science server, they're probably both going to get to run, maybe at the same time if nothing else is going on. But it's completely up to the scheduler. You don't know which one's going to be running. So that's kind of interesting. Let's see what else we're gonna have here. So he talks about it's non-deterministic. He says on some system the parent might go first, on some the child might go first. When I ran this on our computer, it always turned out the same way. So here, let me see if I can go find this. What do I have, 9 minutes left? Let me go find where I'm at. So anyway, hey, I'm gonna run back into HTOP real quick. See these PIDs in the left column? Those are literally the things that return by fork. So anyway, all right, so let's see where we're at now. We wanna do CD, well here, let's see what's in here. So it's the process API stuff we're after. So I'll do CD into C5. See what's in there. I thought, what? Oh, I had capital. So hang on. CD into C5. See what's in there. I think this first one the author was showing was this program 1. So let's run that. Run it a few times. See, our CPU, or our scheduler, I should say, I could do this 100 times and it always keeps running the parent. And I don't know why that is, but it always runs the parent. Here, I'm doing it. Yeah. It's like I'm playing a video game now. Notice the process ID is changing, but it always is running the parent. So the author says it's non-deterministic, and it technically is, but our system is stuck in its old ways, I guess. Let's see what else we have now. Okay, so now the exec. Well, hang on, let's get to the weight. So if you want to make this non-deterministic, the code in the parent can then call wait, and then that forces the child to execute first, and then the parent will resume when the child is done. So basically this wait function, do you remember what it's called when processes communicate with each other? That's a term we should, so inter-process communication. Anybody remember what that's called? I didn't ask it in the quiz because the author just mentioned it briefly. It's called signaling, back and forth. You probably remember that now. So basically, if the parent calls wait, it sets up a signaling channel between these two, and then the child, when it exits its main, it'll send a signal to the wait function that says child's done, and then it allows the parent to resume. So wait, I think, is pretty easy to understand. But let's get to this exec now. What happens if the code, so it would be the code in the child process that runs the exec, right? So let's look at the next one. I think we'll have some code here. Well, this is the one about wait. Here's the one that I simplified my code. He has the 3 clauses. One, if the fork fails, and then if it's the child, and then it's the parent. It doesn't show on my slide, so I did away with the one for if the fork fails. I've never seen it fail. So I just have 2 things: is it the child or is it in the parent? So it's in the. So if the process ID that returned was a 0, you know you're in the child. So it's the child then that runs the exec, and you don't have to. He talks about a family of exec functions. There's like 5 or 6 of them. They all work the same way. They just take different parameters in different formats. This stands for exec vector parameters. So that's why they create a character vector of the parameters, then it's sent to it. So it's all the same. We're just going to call it the exec function. So the exec function happens in the child. So let's suppose we do an exec. Now that's a big deal. What happens to the child process when we call exec? And let's suppose we want to do, the author does exec and he runs the word count program, I think is his example. So let's stick with that same example. So we want to run the exec program on the word count, and we have to send it some other argument on what is it we want to count. So we want to run the word count program, and then we have to have another argument on what we're counting the words in. That's the vector of stuff you send to it. So what happens as soon as we run exec in the child? Ava?
It's gonna rewrite the code.
Okay, we just ran exec in the child. So, boom. The child memory process completely gets wiped out and overwritten with new code. And that code would be from the word count program. Instead, the program counter would get set to 0 because it has to start running. So that gets reset. You get a new stack. And other than that this child process knows to signal back to the parent when it's done, there's no more communication. This is its own thing now. It's like when you move away from home. Your your parents don't have any control except for you signal back when you need money, but that's a different matter. So it runs a completely different program. So that seems weird. Why go through all that work? Why not just fork off a new child that's already doing its own thing, right? It's like in the nature, some animals have babies that can almost immediately walk and run around. Whereas this is kind of like it forks off a child, but it can't do anything for a while. Kind of like a human baby. So, what's the rationale? Why did they just get it right? That there should be this forking process with the original code running for a while, and then this exec process, which completely then starts the new thing. Anybody want to speak to that in our last 2 or 3 minutes? It's one of the central concepts of this chapter. Why that two, here, let's go back to this. Why this fork and then exec? Why not just fork off the new process which is up and running and doing it with its word count or whatever it is? Anybody remember the example that was used in the book? An easy way to rationalize why that is?
Because if, for example, allows to write things to files, like it knows that.
Yeah,
it's
so-
going to do other stuff.
So like if you're like, what kind of program calls for a fork? Well, your shell program does that all the time. Because look here, let me go to my shell and suppose I want to do word count, and I don't know, I want to count the words in some file, right? That's calling a program and passing it an argument, right? That happens in the shell, which is the parent process. Maybe I want to do this with the output. I want to append it to some, maybe I want to dump the output of the word count to some other file. Okay, so what happens as soon as I execute that in the shell, remember that the shell is the parent process in that case. Well, what it first does is the code in the shell, it first opens up a file descriptor that this should be where the output goes. Because standard output comes back to the shell, right? So it can't just immediately execute the word count. The shell first creates a new open file descriptor to that other file that we're gonna write to, and then it does the fork and lets the word count do its thing, where the output goes to that other file. So there's many cases when you run a program from the shell, for example, that the shell has to do a couple things before it lets the child process loose on what it's supposed to do. So they just got it right. The parent program needs to do some stuff usually, and then whatever code is going to run in the child, then it gets a chance to go. And that makes sense if you think about it. Just like I said, in nature, some animals, they hit the ground running on day one almost, but your parents have to do a bunch of stuff to get you able to fend for yourself, and that's kind of what this two-step process is. So anyway, so on Thursday, we get to start talking about how scheduling works. But we're going to start off with something called limited direct execution. It's kind of how the CPU sees a process. And anyway, so, and then we'll also